Thank you for the introduction. My name is Ailina Hardy, and I'm from Lund University from Sweden. And this work was made by me and my two colleagues, Per Hansson and Solveig Melin. Per will be having a presentation right after my presentation. So all right. The outline of the talk, I will start with introducing shortly the nanoindentation schematically. It's a type of test that is, I would say, widely used today in nanomechanics, because from such a test you can determine important material parameters at that scale. Then I would show the molecular dynamic model and the result from that, and the next step will be to introduce the peridynamic theory and comparing actually the two results, or the results from those two theories to each other, and then some final remarks. Okay, this is the description of the nanoindentation test. We have a thin copper coating here with a certain dimension that I will introduce shortly. And then this sphere here, it actually represents the indenter, because the tip of the indenter is, has always a certain radius, even though the real indenters are pyramidically shaped, like Berkovich indenter, but they always end with a tip radius. And we have investigated two different loading directions. So the crystal in those nanoindentation tests have been oriented in two different directions, marked with red here. So we have 0, 10 and 0, 11 direction. The boundary conditions, we have a periodic boundary conditions along the theta and x-axis, and the loading directions in the y-axis. So those have been the settings of the test. The most interesting parameters here are, of course, the dimension, the thickness. Sorry, we should start with the lattice parameter. Since we have copper here, so this is the lattice constant for copper, and then the dimensions of the thin layer. We have the width of 80 A0, which is the lattice parameter, and then 20 A0 is the thickness. The radius of the indenter is about 20 A0 as well. And then we have the indenter velocity here, and the temperature should be somewhere like here. So all the simulations are performed at almost zero temperature. All right, the molecular dynamic simulations. The simulations are performed in LAMMPS, which is a classical molecular dynamic code, and using the embedded EM potential, which has this format here. So this potential consists of two parts, where the first part here, this F here, it's actually, it should be this small F here with alpha. This represents the embedded energy, the energy needed to put an atom into the electron cloud. And then the second term here is a pairwise potential function. We use a canonical ensemble in the simulation with the Nussehuber thermostat. And then the stresses in MD simulations are calculated according to the common procedure used in molecular dynamics. So I don't know how to start this is actually a simulation from the molecular. Let's see. Is it possible to press enter on the computer? Maybe I have to. I don't know how to start the simulation. Is it the play button? Okay. Let's see. Let's hope. Yeah. All right. So this is the result that you usually obtain from MD simulations. And of course, what we see here is only the middle plane of the plate, so this is not fully 3D. Okay, the simulation is in fully 3D, but what we present here is the cross-section of the middle plane. Okay, so now to the peridynamics. Peridynamics is a continuum theory, and I've tried to, in case you have heard the name of peridynamics before, it's actually came from, it's a Greek word. It consists of two parts, where perid means near and dyna force. So what actually peridynamics is about, that we have a non-local force action between the material points. And since we have this non-local force action, we also we don't have any special derivatives of the displacement, as I will show you in the next slide, in the equation of motion. We rather have integrals, and in that way we can actually, or the equations apply everywhere, regardless if we have discontinuity or not. What we can actually say is that this is more or less, you can see the peridynamics as a continuum version of the molecular dynamics simulation, because we more or less have the same structure, even though we operate at different scales. This is also a slide just representing or comparing the classical continuum mechanics to peridynamics. In classical continuum mechanics, we have a local action, so if we look at the material point, we represent the action in terms of traction vectors. In peridynamic theory, we represent that in form of bound forces. And if we have one material point here, then this point is allowed to interact with a neighborhood of material points, not only the nearest neighbors as we're used to in classical continuum mechanics, but here we allow a region, a neighborhood of material points that can interact with each other. And this is represented by this schematic. If this is a schematic picture here, if this is a peridynamic body, then a material point X here, it can interact with a neighborhood, which is usually introduced by, it's actually a sphere. And it is defined by this distance here, delta, which is the radius of the sphere. In the peridynamic theory, it is called the horizon. And what is interesting to say about the horizon is the horizon actually introduces the length scale in the model. All right, if you compare the equation of motion, so this is the equation of motion in classical continuum mechanics, and this is what we have in peridynamics. So we have actually this term here that is written as an integral. It is the only difference between the two equations. And then if we go to the state-based peridynamics theory, we would like to introduce some kind of stress tensor which we recognize from the classical continuum mechanics. So T here then in peridynamics is a force vector state field which actually maps the bond between the two particles. All right. Now, the questions that we try to answer is, can peridynamics be efficiently reproduced, that results that we can obtain by molecular dynamics? And the reason why we want to do that is, of course, to save computational times, because the molecular dynamics simulations are usually very demanding, time-consuming simulations. And since we have looked or investigated two different directions, so in the MD simulations, those are schematical pictures of 4 unit cells. So in direction 0, 1, 0, we have this kind of orientation. In direction 0, 1, 1, then the same 4, or the same, the 4 unit cells will look like this. And when we have done that, we have introduced the peridynamic model, which is more simpler. It's only points, material points, which are placed in a central cubic configuration. And then we have also used the same distance between the two material points as the size of the unit cell in copper. And making this simplification, it actually results in reducing the material points here compared to the number of atoms down to approximately 25% of the initial number of atoms. Peridynamics is a continuum theory, so we represent everything by, or we have to introduce some material parameters, and in this specific theory that we have used here on this specific model, we have 2 elastic parameters, 3 plastic parameters, and then the horizon, which introduces the length scale in the model. So what we have done then, we started with the molecular dynamics simulations and then tried to extract elastic parameters from that, and then use those elastic parameters in the peridynamic model and try to calibrate the rest of the parameters that we have in the model. The typical results that we obtain or we want to reproduce from the nanoindentation test are the force displacement curve. And what we see here are force displacement curves for the 2 orientation. 0, 1, 0, it's that one here, and then here we have the second orientation, 0, 1, 1. The red curves are the results obtained from the MD simulations, and the blue curves are obtained with the peridynamic simulations. What I didn't mention is that the peridynamic model they're also implemented in LAMMPS, since both MD and PD models have the same structure. So the peridynamic models or simulations are also performed in LAMMPS. From such a curve, one can extract, for example, the Young modulus. The Young modulus is usually determined from this slope here. And another parameter that's interesting, also the hardness. Those curves are usually used for extracting those 2 parameters. We also compared the arrangement of the particles during the test. So what you see on the left side here is molecular dynamic simulation. On the right side are peridynamic simulations for the orientation of 0, 1, 0. And 3 different displacements where A0 is the unit cell, the size of the unit cell. And we can see the similarities between the 2 simulations, where you can see the orientation, the atoms here, this angle here corresponds to 45 degrees. You can also clearly see the periodic boundary conditions from the simulations. And the second result here is the second orientation. Here again we see those slip bands. Actually, they are also oriented in the same direction, which is 0, 1, 1. But in that case, this is the loading direction, so that's why those bands are oriented in that way. If you compare, if you go back here, this direction, those directions are 0, 1, 1. In that case, 0, 1, 1 corresponds to the loading direction, so the shear bands are oriented in that way. So then to the conclusions, or final remarks. We started with molecular dynamic simulations, which were used as a reference simulations, and try to investigate to what extent the peridynamics can capture nanoscale features. What we can see about the result, we have quite good coinciding distributions, or especially the force displacement curve could be reproduced in a very good way, and meaning that from peridynamic simulation we can actually extract important elastic parameter as Young modulus and Hahn using the Oliver parameter, for example. And the final conclusion is that we can efficiently reproduce those results with significant reduction of the degrees of freedom. Thank you.
Thank you so much.